So there are different techniques to formulate the contact force vectors. Those are not straightforward when we look at the complex geometries that we are handling in the finite element method. So we have got the different algorithms for the calculation of the contact forces and to formulate the contact problem itself. So we have got, basically there are two, pure penalty and normal Lagrange approaches. There is one more which is combination of two, is augmented Lagrange method, right? So we'll discuss these three formulations briefly in today's webinar. So I'll firstly discuss about the pure penalty algorithm. So what happens in the pure penalty algorithm is we have got this normal force we need to calculate. So if you look at here in this example, the gray body and the purple body, the pure penalty algorithm kind of prepares a spring. It forms a spring with the stiffness based on the properties or the metal properties of these two contacting bodies. So it calculates, so it considers the Young's modulus of those two bodies while calculating the contact stiffness or the contact stiffness or the K value. We'll just keep that value, keep this word K normal. So it calculates the contact stiffness based on these properties. We have got this some kind of a penetration in the body when the two bodies are kind of going inside each other. That time, that K into deformation, whatever it is getting, that gives the contact force in the normal direction. So that is if I'm applying force from a force of F value from the top, because of this spring stiffness and the deformation or the penetration, there will be an opposite force which is opposing the penetration of this gray body into the purple body by K into the penetration. Similarly is the case for the tangential direction. So we have got this tangential stiffness and we have got this how they are relatively moving, how much distance from each other. Like it's not the penetration, it's a relative sliding between the two. Based on that, it calculates the force in the tangential direction. So you can see in this equation, if we move this particular term to the right, it becomes F minus, right? So if direction is downward, the K, the N, the normal direction force will be opposing the motion of the F. So this is negative. When it comes to the left side, it becomes positive. And this is my gap function, and this is my, coefficient of friction. So the main thing over here is my contact stiffness is constant. It is a function of the spring, or it is a function of the material stiffness of the body, and which gives the constant value over the period of a time in the simulation. The advantages of this particular method is it can give rise to some kind of a penetration in the body, but it helps in the convergence because it's a simple method. We have got the stiffness, it is modeled as a spring, and we have got this penetration. It's easy. It can easily calculate the stiffness multiplied by the penetration, and it can easily calculate the contact force. Helps in the convergence. So I don't want a penetration in the body. So what I can do? I can go ahead with the normal Lagrange method, in which there is zero penetration. Right. So we have got the normal contact force as a function of additional degree of freedom that is present on the surfacing or on the elements or the nodes which are in contact. So those nodes will be solved for the additional degree of freedom. So if you remember in the finite element method, each node has certain degree of freedoms, right? So there will be an additional degree of freedom which we need to solve if we are going for the normal Lagrange method, right? And that degree of freedom doesn't allow to penetrate one body into the other, but it comes with the cost. It is computationally expensive because there is no penetration, right? And it is more accurate as compared to the penalty method, but it is not allowing it is not allowing any kind of a penetration. It is going to hit the surface and the contact. If there is a contact, it will again, like there in the next iteration, there will be normal force which is kind of pushing the bodies away from each other to avoid the contact. Then again it will come into contact. Then that kind of process happens, contact no contact, till it kind of stabilizes the contact. So that gives rise to the chattering problem in the normal Lagrange method, and which gives rise to which may lead to increased number of iterations, and in worst case scenario the solution may not converge also, right? So that is the problem with the normal Lagrange method, but it's more accurate, like it's most accurate algorithm the finite element solvers have right now. Like it is independent, like Ansys, Abacus, anything you take, normal Lagrange is the most accurate solver you can get, but it comes with the cost of convergence and solution time, computational time. We have seen the penalty method also. This is the right figure over here is a penalty method. So it allows some penetration. It doesn't consider the contact boundary as very rigid. It allows some penetration and it solves like, yeah, it is fine. If there is some penetration, it is fine. I'm getting a solution, right? But what if we don't want the penetration that is created by the penalty method? For that, we have got a sweet spot of augmented Lagrange. So what it does, it takes best of both methods, and it kind of calculates the contact stiffness based on the based on the metal properties, as well as it calculates the Lagrangian term, which is used to calculate the contact force, right? So we are not going to details of how that Lagrangian term is calculated. It's kind of a similar Lagrange term what we have seen earlier. So that kind of a Lagrangian term is calculated based on the penetration of the one body into the other. So as the penetration changes, the Lagrangian term, if the penetration is large, Lagrangian term will increase and push out the surface from the penetrated area. That's how it changes, and it kind of it gives more control to the solver over the penetration, and it is like it gives a fairly accurate results with enough number of iterations. So the iterations, the equilibrium iterations, as we have seen in that, Newton-Raphson from one point to the other point, those iterations are kind of more than pure penalty method, but surely it will be less than the normal Lagrange method. And we get enough accuracy with the augmented Lagrange method. So if we talk about the Ansys commercial software, it is generally preferred like to go ahead with the augmented Lagrange in the frictional contact. In other software solutions like Radios or you take Abacus, so what they have done is like they generally, there are two algorithms and they generally prefer pure penalty algorithm because their pure penalty is good enough and it doesn't allow a lot of penetration into the bodies. So it depends upon the software developers which algorithm they want to like, what settings they are doing. In Ansys, pure penalty is kind of giving more penetration. In Abacus, pure penalty gives enough penetration, so you can go ahead with the pure penalty. But if you are using Ansys, go ahead with the augmented Lagrange method. So that through this we are calculating the contact force, which goes back into the contact formulation, and which goes back to the stiffness matrix, and it's solved with the help of different solution techniques, the finite element method. Right. So all of this we have discussed till now is on the relative sliding, and there is a contact force, there is a change of a contact force that is happening. What if I have bonded, like what if I have a welded connection between the two plates, right? So you might have seen tightly bolted connections between the different portion of the body of, or like I have a blades. If you look at the wheel or the blowers, right? So their blades are kind of welded on the frame or on the shaft. So there is no relative motion. How to model that kind of like we cannot make it a one body, right? When you can make it a one body, but that it may change the physics of the problem, or just the weld is there, you want to model the weld, or permanent connection, there is no relative sliding between the two bodies, you want to go ahead. So in those cases, you create a multi-point constraint. What it does is kind of it writes an equations, or it constrains the degree of freedom on this I, J, and L node with respect to the node, or we can name it as a K node over on this blue body. So it directly maps the degree of freedoms on these nodes to this node, or if it is like it can match the degree of freedom from K to other three nodes also, or from three nodes to K, right? So that kind of a simple mapping of the degrees. If you look into the manual detail, details of the manual of the different softwares, they even mention that the degrees of freedom are deleted on some of the nodes when there is an MPC is written in the in the softwares, just to If you have a lesser degree of freedom, lesser number of equations, less solution time. It's a technique that softwares are following to maximize the minimize the computational time and maximize the utility of the software. So this is the MPC constraint. It is generally used in the bonded contact. Some tie constraints are there in other softwares. So it is similar to the tie constraint. Okay, degrees of freedom are directly mapped from one to the other. It is different than penalty, it is different than Lagrange, and it is a linear, just an equation we have to solve, and it just matches the degree of freedom on the two nodes. It is generally used with the bonded contact. That's the thing. I think it is sufficient for while studying the theory of the contacts. Okay, so we have gone. We have understood how the contact force is calculated and what are the different formulations that are being used. We have got the contact stiffness. We have got the contact force out of it. But if I can change that contact stiffness, I know the penalty has calculated some stiffness, Lagrange method has calculated some stiffness, but my solution is still not converging. I need to understand I need some more control on the stiffness. So what to do? We can change the normal context or the normal stiffness factor, right, in the solution itself. So fkn is 1. When the fkn is 1, whatever stiffness is calculated by the software, that will be used directly in the solution. But if I want to change that factor, like if my calculated stiffness or the force is some x, I want to reduce that force just to achieve more convergence, and I'm okay if penetration is there, but what if I want to achieve more convergence, like easy convergence, you can reduce the FKN. We will revisit those points later on when we are discussing the contact convergence. The main point I wanted to discuss in the normal stiffness is that it is a factor which is multiplied to the contact stiffness that is calculated by different methods, as per the user's requirement. For the default problems, FKN is 1. For bonded contact, no separation contact, FKN is 10. That is enough till now. We will revisit this point again at the end of this lecture. Then we have got the contact stiffness update, right? So we can update it at each iteration. If we don't update it, whatever the contact stiffness is calculated in the first iteration itself, it will be used for all other iterations, all the remaining iterations of the solution. But it is obviously, as we are not calculating the contact stiffness on each iteration, computational time will reduce, but accuracy will be affected. Then each iteration we can use, or each iteration aggressive, right? So both of these controls gives more update, or the more control to the user to update about the contact stiffness on each iterations. If you keep it program controlled, it will update on each iteration, and it is more accurate. It is recommended to update the contact stiffness on each iteration, so that the contact uses the latest information, and you will not observe any kind of a patches or kind of a penetration at the end of the analysis. So I think we have covered contact formulations, how that nonlinearity is there in the system in the finite element method with respect to the contact. Then we have gone through the normal stiffnesses, how that normal stiffness is updated, and all those terms. So we'll not go into details of how that where to define the different parameter detection methods and other parameters in the contact, right? So we are just discussing about the theory. Now we will discuss the convergence issues. So we have defined the contact. We have defined that even if we have defined the normal Lagrange, it is not converging. Augmented Lagrange, it is not converging. Pure penalty also, it is not converging. So what are the convergence problems? Like, what are the general reasons behind those convergence issues? We'll discuss now. So the first is unit system. So generally check while solving, like Ansys Workbench has made it very easy. Like you don't have to worry about the units when you are modeling any problem. In other softwares, you need to have a sync of the unit system what you are using. The simulation software doesn't have any standard units of its own. What we need to do irrespective of any software, you need to check for the unit system, like a component of 10 simple cantilever beam of length of 10 mm cannot be under 1 ton of a load, right? So that will give rise to issues like rigid body motions, or solution will not converge itself. The contact will not take place because of the huge amount of contact force that is being generated. The contact is not able to handle that amount of contact force in the iterations. So you just make sure whatever force values you are applying, those are logical. Then elements quality, you need to make sure that elements are of a good quality when there is a contact. Like big elements with very less number of nodes will not give you the convergence, or will not give you the fair contact force distribution also when they are coming, when we are defined, when they are defined in the problem. Mesh sizing. So mesh sizing is important when we are defining the two contacting surfaces. I'll briefly tell you, like target and contact. We generally use these terms while defining a contact. I have the target and I have a contact, or I have a master and a slave, right? So generally contacts or slaves are finely meshed as compared to the targets or the masters. So the mesh sizing should be enough so that the nodes on the contact, when they are coming and searching the respective nodes on the target, though the nodes should be able to find out each other, right? So it's like the one node is coming, and where is the respective nodes? He wants to write that constitutive equation. He wants to transfer the force from one node to other, and if he is not able to find out that node itself, it will penetrate into the body, right? So the nodes should be enough to transfer the forces. There should not be elements of the site should be enough, small enough to, when they are sliding, at least 3 to 4 elements should be there when they are sliding. Unless and if it is just a one node or two nodes coming in contact with the one node, it becomes challenging for the problem to identify and to go through that iterations and write those equations. So maintain your mesh properly. Then the detection methods. Detection methods is kind of a when the node is kind of one node or the one Gauss points on one body or the one element is coming in contact, how they are trying to find out the respective Gauss points on the nodes on the other surfaces. So detection methods are kind of different based on the softwares. In Ansys you can check on the Gauss points. In Abacus also you can check on the Gauss points to Gauss points, or from the nodes to nodes. Anything is fine. So those techniques also affect the solution accuracy or the convergence issues in the contacts. So if I'm checking if there is a sharp corner, and in the sharp corner we have only one node, then a sharp corner is in contact with the flat plate, and we have only one node, and I'm detecting at the Gauss points. So Gauss points are generally inside the element, right? Inside the element. And the nodes are on the exterior body or exterior surface of the element. So even if the node is in contact with the surface, Gauss points are not there in the contact. So there will be some penetration happening, and then only this contact detection will happen. So all these factors just affect the convergence of the system, or the convergence of the contact problem. So the solutions I have already discussed for some of the solutions. The main solution that generally you might have seen people following is that reduce the FKN value itself, the contact stiffness. You reduce it to like 0.1, or 1 is the program controlled value. Reduce it to 10% or 1%, like that. If you reduce it, yeah, you are going to surely get the convergence, because that sudden abrupt change that we have seen, that red line was there, the abrupt change that is happening, the contact force that is being generated will be less if you reduce the FKN value, but it will give rise to a penetration. So what we need to do, if you are reducing that penetration value, or if you are reducing the FKN value, you need to check the penetration at the end of the analysis. Generally, whatever units you are working, 10 raised to minus 3 or 10 raised to minus 4, those kind of units, those kind of like deformations, or penetration, you need to check at the end of the analysis. In some cases, we need to increase the FKN value also. Like if materials are soft and they are kind of penetrating within each other, there we can use we can increase the FKN value also. but those are very like few cases when if you are most of the people are using like steel and other components, that time FKN generally we reduce. The next point is apply load slowly by increasing the load steps. So what happens, as we have seen in the Newton-Raphson method, as we go on solving the problem, if we apply a huge load or like a large amount of load in the first load step itself, the contact is not able to balance that force, and the two surfaces will penetrate within each other and doesn't solve only. It doesn't detect the contact. Even if you get the solution, the contact will not be detected, right? You might have come across this kind of scenario, like problem is solved, I have applied the force, but contact itself is not detecting. Two surfaces are penetrating within each other. The force transfer is not happening. That is because of the applied load step is high. We need to increase the load slowly in small increments. So that is the kind of technique you can follow. Increase the substeps. Increase the substeps in the model. Refine the mesh on the contacting surfaces, and last is the correct use of a contact formulations. Like I was saying, Lagrange will give you more iterations, more convergence challenges. So use correctly the contact formulations. What is recommended for Ansys is augmented Lagrange. What is recommended for Abacus is pure penalty method. So that kind of a formulations you can use while solving the problem, and you can get the converged solution. Again, you need to check the penetration at the end of the analysis using the output controls, and then decide if it is solving rightly or not. So with this, I'm concluding today's lecture. I have one example I just wanted to go through before concluding this today's webinar. I have solved one problem. This is a plate, and this is a small plate which is coming in contact and hitting the it is coming in contact and hitting that bottom plate. So what if FKN is 1? The middle figure is FKN 1, in which my solution is not converged after 8 iterations also. But if I reduce the FKN to 0.1, I am getting solution in a very short time, third iteration itself, with no bisections occurring. Right, bisections are basically the load is been reduced. So the force, I have applied a 5 Newton of force, it is reduced to 1 Newton or less than 1 Newton, but still it is not solving. So this is the effect of FKN that happens when we are when there is a high contact stiffness, and when we change the contact stiffness. So these are generally the convergence issues I wanted to discuss today with all of you, and the theory that I wanted to discuss in today's webinar. So it is a brief introduction. There is a lot of theory goes behind. Apart from this also, like what are the different equations, how they are solved, what is the Gauss points, how those Gauss quadrature equations are. But that's not part, like it will take a lot of time. In one, whatever the points we have discussed today, those are useful for you when you go and visit your problems, whatever you are solving. These points will be useful for you to get the correct solution with enough accuracy in your problems.